And in reality, only something like Mathematica or some other computer code can do the really hard surface integrals. In this class, we're going to look for simple geometries that we could do these integrals by hand. Okay, so what do I mean by simple geometries? Okay, basically our goal is to pick surfaces where the electric field is either parallel or perpendicular to the surface. So the direction of it is either parallel or perpendicular to the surface, which remember we defined by that infinitesimal dA vector. And this has to be true all along the surface. Remember, we need a closed surface, so all along those closed sides. Okay, that's one of our goals. The other one is it's nice if the electric field is constant along the surface as well. Okay, well, this can be a little bit more general. We can just say along each side of the surface. So in this point, it's important to remember that these surfaces that we're choosing to do this integral on, they're not real objects in space. So I just want you to imagine like a charged sphere, like a Van der Graaf. If I wanted to somehow figure out how much charge was on that Van der Graaf, I can pick an imaginary surface and put that around it and calculate the flux through that imaginary surface. So we can really pick any surface we want as long as it's surrounding the charge that we want to know about. So either part of the charged surface or the entire charge itself, okay? So let's do some examples. The first example, we'll just do a plane of charge, and we'll make it even simpler. We're going to make it an infinite plane of charge, which means that the sides are going to infinity. And of course, that seems unrealistic, but you can assume that a sheet of charge is an infinite plane of charge if you are either really, really close to it, okay, or, right, it's just really a big sheet and you are near the middle, okay? So basically you're trying to get away from those edge effects. We're going to give this sheet a positive charge, so we can describe it with a surface charge per area, which we said is sigma. If I look at it from the side, right, it's going to be a thin sheet of positive charge. This is the side view. And remember, the electric field is going to point in the direction that a positive charge would move. So it's going to point up here in this particular part near the plate, above the plate, and it'll point down below the plate. So if you put a little test charge there. So I'm going to pick an object that has the electric field either perpendicular or parallel to the sides of the surface, okay? A typical surface to choose for this particular configuration is called a pillbox. That's a fancy word to say I'm going to pick a rectangle. You could also pick a cylinder if you wanted to, okay? But we'll use the pillbox. Okay, so the pillbox, let's see if I can draw this. Well, we'll do the cylinder. That'll be easier. Okay, we've got a cylinder here. It's going to intersect the surface. Okay, and I can draw it here on the other side. Okay, so the surface is actually going through my pillbox here. The part of it that's intersecting my surface has an area that I'll just call A. Okay, and the amount of charge enclosed in this case, so this is, we chose a pillbox. I'll write this out. Pillbox or cylinder, and this is what's called a Gaussian surface. It's an imaginary surface that we're using to do math. Okay, this particular surface, the amount of charge we have enclosed is going to be equal to our charge per surface area. That's what this is. So remember, this is the charge per area times the actual area we enclosed. Therefore, Gauss's law tells us that the electric field dotted with if we take the surface integral around this closed surface, this pillbox, okay, it should be equal to, right, our enclosed charge divided by epsilon naught, which in this case would be our sigma times A divided by epsilon naught. Okay, what are we going to use this to do? Well, we're going to use it to actually calculate the electric field. Okay, these surface integrals, I can do them one side at a time. Okay, so I'm going to take my surface integral here, and I'm going to take it one side at a time. I'm going to do the integral over the top, and I'll also do the integral over the bottom. And I'm going to add that to the integral over the sides. Okay, so if I do that piece by piece, I'm calculating the total flux through all of the surfaces. Okay, so if I look at my cylinder here and think about it more carefully, okay, the dA, a little bit of area on the top, is going to be pointing straight up. Okay, if I draw the sides here, on the sides, a little bit of surface area will be pointed just perpendicular to the side, so it would be radially outward. And then at the bottom, if I were to draw a little bit of surface area, that's going to be directed straight down. Okay, so if I look here and I compare this to my field, okay, I'm going to draw the side view here of what the pillbox would look like. Okay, here the dA and the field are parallel. Okay, here they're parallel, and everywhere on the sides, the electric field and dA are going to be perpendicular. Okay, so what does that give us? Well, because of that, I've got the electric field at the top. They're perpendicular, so I can just get rid of that dot product because those two guys are in the same direction. Same thing here. Okay, and this one is just going to go to 0. Because the electric field is constant for each of these integrals, I can actually pull it out. Okay, so for here, I would get just the integral over dA. And of course, same thing over here. Okay, the areas are the same for both of these. And so I end up here with just 2 EA, okay, and all of this is equal to sigma A over epsilon naught. Okay, so if I put this all together, then I get 2EA is equal to sigma times the area over epsilon naught. I can use this to solve for the electric field. A's are going to cancel out, so it doesn't depend on the area. And I get that the electric field is equal to sigma over 2 epsilon naught. Okay, and if I want to include the direction there, it's always going to be normal or perpendicular to the surface. And then it points up or down depending on whether you are above or below. Okay, it might be surprising to you that this electric field doesn't depend at all on the distance you are away from the plane, okay? So if I go back here, by the way, I didn't really mention why you can argue that it's straight up rather than at some angle. Hopefully it makes sense to you that it has to be straight up due to superposition. For example, the horizontal components of the electric field from this charge at this point would be canceled out by the horizontal components of the electric field from this charge. So it should be straight up, okay? But why is the electric field the same here as it is here, as it is here? Well, the reason for that has to do with the fact that we're dealing with an infinite plane of charge. So one way you could think about it is if you've got a point that's really close to the surface, it's feeling a lot of electric field or strong magnitude from the charges that it's close to. Okay, so you get a certain amount of electric field, and that depends on the density of charges in that part of the sheet. Okay, as you move further away from the sheet, okay, obviously you're not get as close to those charges that you were close to, but you are getting more contribution from the charges that are further away. Okay, so now you're kind of equally close to a lot of charge. And when you add up the electric field from all of those charges, it actually ends up being the same as the electric field from just this little bit of area that you were close to before. Okay, so if it's really an infinite plane, the electric field is pretty constant. Once you get, of course, in a real plane, once you get near the edges of your real life plane that's not infinite, this particular assumption fails. But it's not bad as long as you're close to the surface of a pretty big sheet of charge.